All right, let's just jump right in. We live in a world that is completely built on software, right? It's in our phones, it runs our power grids, it's everywhere. But as this software gets bigger and more complicated, how do we actually know it works? Like, really trust it? Well, today we're going to look at a really powerful concept designed to do just that. It's called modular verification. This quote really just hits the nail on the head. It's not about fighting complexity with even more complexity. No, it's about taming it, about bringing a logical order to the absolute chaos of millions of lines of code. And that, right there, is the million-dollar question, isn't it? I mean, checking a few hundred lines of code, sure, that's one thing. But how in the world do you prove that a massive system, like an entire operating system, is correct without getting hopelessly lost in the details? So here's how we're going to break it down. First, we'll look at just how big this challenge really is. Then, we'll get into the main strategy, this divide and conquer idea. After that, we'll unpack two really powerful mathematical tools that make it all happen, and we'll wrap up with where this stuff is actually being used out in the real world. Okay, so first things first, you gotta appreciate the sheer scale we're dealing with. Modern software isn't just big, it's this incredibly intricate web of interconnected parts. Trying to verify the whole thing in one shot, it's practically impossible. So instead of trying to tackle this impossibly huge problem all at once, some very smart people came up with a divide and conquer approach. And that is the absolute core idea behind modular verification. So here's the key takeaway. You take this giant, complex beast of a system and you break it down into smaller, bite-sized pieces, or modules. Then you prove that each one of those little pieces works perfectly on its own. And then, this is the clever part, you use those individual proofs to build up a larger proof for the whole system. It's a truly brilliant way to manage what would otherwise be totally overwhelming. The whole process basically boils down to 3 steps. 1, you deconstruct the system, break it into logical, independent chunks. 2, you verify each of those chunks, each module, by itself. And 3, you compose, or kind of stitch together all those individual proofs to guarantee the entire system is solid. And you should know, this isn't just some clever project management trick. It's built on a super solid logical foundation called axiomatic semantics. Think of it like describing what your code should do using pure mathematical rules or axioms, instead of just running it and seeing what happens. This lets you prove a program is correct by analyzing it piece by piece, sometimes even statement by statement. The level of certainty you get from this is just incredible. Okay, so that all sounds great, but how does that stitching together of proofs actually work? I mean, logically. For that, we need a couple of advanced tools from our toolkit. The first one is a concept from pure mathematics called sheaves, and it gives us this amazing local-to-global superpower. Sheaf theory is the formal math that really makes this whole thing possible. It's like the instruction manual for composing our proofs. It gives us the rigorous, undeniable rules for how we can be certain that something that's true in one small part can be combined with other true parts to prove something is true for the whole system. Probably the best way to get your head around this is with an analogy. So imagine you want to create a perfectly accurate map of the entire world. You wouldn't try to draw it all at once, right? No way. You'd start small. You'd make a super detailed local map of just a single town, and you would verify that every single street, every landmark is absolutely perfect. Once you've proven that first little map is flawless, you move to the town next door, and you do the exact same thing. You rigorously verify its map, all by itself, and you just keep repeating this process for every single local area. And here's the magic. Because you know each individual local map is perfect, you can stitch them all together with total confidence that the final, complete, global map is also correct. That is the essence of what sheaves give us. Local correctness guarantees global correctness. It's a huge deal. So we have a way to structure the problem, which is great. But the proofs themselves can still be incredibly complex and messy. And that brings us to our second tool, geometric logic, which is all about making the act of proving things way smarter and more efficient. Geometric logic is another one of these frameworks built on mathematical rules, but its specialty is analyzing proofs. It's specifically designed to be easily understood by computers, which makes it absolutely perfect for automating the process and just generally making verification much, much cleaner. So what's the real-world payoff here?
Well, traditional logical proofs can get super bogged down with all these extra redundant steps. Geometric logic, on the other hand, lets us create what are called cut-free proofs. That basically means it gets rid of all the unnecessary logical steps. Those are the cuts. And you're left with proofs that are simpler, cleaner, and way easier for a computer to handle.
All right, so we've talked about these powerful, kind of abstract tools, sheaves and geometric logic. But where does the rubber actually meet the road? Let's take a look at where all this theory is being used to build software we can actually trust. And look, this isn't just some academic exercise. These techniques are used to verify the absolute foundations of our digital world. We're talking about the very heart of operating systems, that super low-level machine code that your processor actually runs. It's even used to tackle the nightmare problem of concurrent programming, where lots of things have to happen at the same time without breaking each other. This is absolutely mission-critical stuff. At the end of the day, that's the bottom line. These advanced logical tools are not just some fun curiosities for mathematicians. They are absolutely essential for building a digital world that we can depend on, giving us a rigorous, scalable way to prove that the software running our lives is actually correct. And that just leaves us with this one final, really fascinating question to think about. As our systems get even more complex and we start relying on AI and autonomous systems, these tools are only going to get more critical. So it makes you wonder, what's the next logical leap going to be? What new ideas will we need to keep making our code truly trustworthy?